start. So we have to start question number 4. One comma 3 dichloropropane 2-ol is made by reacting M. So if you look at M have a C over here. So this part is indicating me a ketone, and it is further an alkyl halide or halogenoalkane because it have a chlorine in it. And if you see it is alcohol, as OH is bonded to a carbon, alkyl halide as well. So what they are asking, give the systematic name of M. Okay. So if we see over here, the rules that we have discussed, we first select the longest chain. So it can be my longest chain of a 3 carbon atom, then assign the number with the functional group closest. So I can start with any one side. So this is carbon number 1, this is carbon number 2, and this is carbon number 3. So chlorine is always written in the prefix. So it would be 1, 3 dichloro, because there is a 1 chlorine on the first carbon and the second chlorine on the third carbon. And then it's propa, non-prop for 3 carbon atoms and on for having a ketone. Is this understandable? Now, name the functional group present in M that changes during the reaction. So we already identified that there is a ketone which is converting into an alcohol. So the functional group that changes, ketone, or you can write carbonyl as well, but ketone is the most appropriate answer. Now in the next part, they are asking you to state a suitable reagent for this reaction. So if you try to figure it out, you will find that a ketone is converting into an alcohol, which means it is a reduction reaction. And in this reduction, we can either use NaBH4 as a reducing agent, or we can use LiAlH4 in dry ether. So we can write any one, because any one that is either NaBH4 or LiAlH4 can be used as a reducing agent to reduce a ketone or aldehyde into alcohol. So NaBH4. Next part. Separate samples of 1, 3 dichloropropane 2-ol and 3 chloropropane 1, 2 diol. Okay. Are heated with the excess acidified dichromate until there is no further reaction. In each reaction, the different organic product Q or R is made. Okay. So if you look over here, if I am using, as they have mentioned, acidified dichromate. So dichromate is an oxidizing agent, which means this reaction is an oxidation. And this one, if you recall, is a secondary alcohol because the OH bonded to a carbon, that carbon is further bonded to 2 carbons. So whenever an alcohol is oxidized, a secondary alcohol is oxidized, a ketone is formed. So there is this change in the structure. Rest of the structure remains same. So I have figured it out. Is this understandable to everyone?
सर पार्ट ए में बेसिकली सब्स्टिट्यूशन हो रही थी ना?
It is reduction, not a substitution, because see, ketone is converting into an alcohol, that is a reduction reaction, and when alcohol converts into a carboxylic acid, aldehyde or ketone, that is oxidation.
सही है सर.
Okay. Now, here again, we are using acidified dichromate. And heated. They are saying heated, so it means it is heat under reflux in both the cases. So again, it is an oxidation reaction. Now, if you see this structure, 3-chloropropene 1,2 diol, this alcohol is a secondary alcohol, and this alcohol is a primary alcohol. So if you recall the oxidation of alcohol, when primary alcohol is heated under reflux, it turns into carboxylic acid, and secondary alcohol on heating under reflux turns into ketone. So here I just put a C double bond O, and here there is a C double bond O and an OH as well, because this was the primary alcohol, so it turns into carboxylic acid. So I have figured it out what is to everyone. Okay. Now what they are saying, Q and R are tested separate 2,4 dinitrophenyl hydrazine solution, that is 2,4-DNPH, and sodium carbonate solution. Okay, let me recall you. It is that for carbonyl. And when I say carbonyl, it means we are referring to either aldehyde or ketone. And sodium carbonate gives a carbon dioxide gas with a carboxylic acid or any other acid. So among the organic compounds, sodium carbonate reacts with carboxylic acid only. So it can be used for the test for carboxylic acid. And the observation for this reaction would be effervescence or bubbles. And the observation for this reaction would be orange precipitates. So they are asking for the observation of 2,4-DNPH with Q and 2,4-DNPH with R. If you see, Q also have a ketone present in it, and R also have a ketone present in it. This is ketone. And here, this is ketone. So both the compounds contain ketone. So it means I'm going to observe the orange precipitate with when Q is treated with 2,4-DNPH, and same orange precipitate when R is treated with 2,4-DNPH. Is this understandable to everyone? And if you see further, when we are adding sodium carbonate with Q and R, that Q have only ketone and carboxylic acid. Is not present in Q, but carboxylic acid is present in R. So here there would be no change. So I may write that no visible change, because if we mix them, we are not going to see anything happening. But when we add sodium carbonate to R, that carbon dioxide would form, because R have a carboxylic acid, and sodium carbonate, when reacts with any acid, it gives off carbon dioxide. And as the carbon dioxide is formed, you will going to observe bubbles or effervescence or fizzing. So I can write any one. Either I can write effervescence, I can either write bubbling, either I can write fizzing. Is this understandable?
Yes, sir.
Okay. Now, okay, great. Citric acid can be made from M in four-step reaction. Okay, so that is citric acid. Okay, I'm going to draw this. So if you look at step one, let me draw both the structures here. If you see C double bond O, I'm not making the whole structure. I'm showing the structure where the change is observed. That C double bond O have an OH and C triple bond bonded to it, right? If you see, there is no other change. On both the sides, I have CH2 then bonded to a Cl. Here as well, CH2 bonded to a Cl, right? So this reaction, if you try to identify this reaction is nucleophilic addition to a carbonyl, and a nucleophilic addition to a carbonyl is done when we add HCN along with NaCN. NaCN basically catalyzes this reaction, and this reaction is nucleophilic addition. Okay, first we will work on this, then we will look at the questions what they are asking. Now, if you see in step 2, let me highlight those area where the change is seen. This is converted into this. Okay, now if you look at the product of the step 2, this carbon and this OH, if you see, remains same. This structure remains same. That CH2 bonded to Cl, and here CH2 bonded to Cl. But this carbon nitrogen triple bond is actually converted into carboxylic acid. So if you see, the change is in this part, and a nitrile converted into carboxylic acid. So if you recall the reaction, that is a hydrolysis, and as carboxylic acid is formed, so I can consider it as an acidic hydrolysis. So we can put the reagent that is acidic medium, or I can write HCl, or I can write sulfuric acid. And for hydrolysis, we need to heat the solution. So this reaction, step 2, is hydrolysis. Now let's move to step 3. If you see at step 3, the change we are observing is this. This carbon chlorine here, instead of chlorine, we are observing a nitrile on both the sides. So if you recall this reaction, that is a nucleophilic substitution reaction, which is done when KCN, ethanolic, or KCN in ethanol, is used along with heat. So if you see over here, the whole structure remains same. There is a C, and this carboxylic acid is over here, and here that we got a C triple bond, and after CH2, and here we also got a C triple bond N. So if you see, these parts are changed into this. Is this understandable? Now in step 4, if you see, these C triple bond N are converted into carboxylic acid. So again, there is a hydrolysis, the same reaction that occur in step 2, right? It's an hydrolysis where, and acidic hydrolysis, because we are getting a carboxylic acids, not their salts. So we can either use acid and water, any acid, or a HCl or a sulfuric acid, and heat it. So now we are doing with our homework. Now let's look at the questions. Complete the table for each step of the reaction sequence to identify the reagents and the conditions required. Okay. In step 1, what we have identified, what reagent is needed? HCN and NaCN, which is a catalyst. So the condition is catalyst. Type of reaction, we have identified that it is nucleophilic addition. Now let's look at step 2. They have provided you dilute sulfuric acid. And now you have to write the type of reaction. So what we have decided that it's an hydrolysis. So I may write hydrolysis over here. Now in step 3, if you see, we have used NaCN and the condition is ethanolic. So I may write NaCN, or we can use KCN as well. See, KCN or NaCN. I have put a KCN over here, so I can write KCN and in ethanol. The type of reaction we have decided is NS, which stands for nucleophilic substitution. Now, step 4, again dilute sulfuric acid is used, and we have decided it's also a hydrolysis, so I may write hydrolysis over here. Yes, is this understandable to everyone?
Yes, sir.
Okay. Now, compound X contains the same functional group as a citric acid. Okay. So if you look at citric acid, we have, in citric acid, we have an alcohol. And if you look at more closely to the alcohol, the carbon which is bonded to OH have a carbon over here, have a carbon over here, and have a carbon over here. So it is more specifically a tertiary alcohol. Beside this, the other functional group that citric acid contain is a carboxylic acid, right? Okay. Now, the table describes some of the similarities and differences between citric acid and compound X. Okay. Citric acid have a no chiral center, but X have a chiral center. 1 minute, please. Okay. Reaction with Na, and both observe the fizzing. And with sodium, both alcohol and carboxylic acid react. So, and as they have told you that these both functional groups are present in X as well. With acidified dichromate, if you see what they have told you, that it remains orange and it turns into orange to green. This information would be very helpful. Why it remains orange? It is because in citric acid, what we have decided that the alcohol is tertiary, right? And tertiary alcohol never oxidizes. That's why it remains orange. And here that it turns into orange to green. So from this, what we can conclude that in the alcohol that is present in X is either primary alcohol or secondary alcohol, but for sure it's not a tertiary alcohol, because if it is a tertiary alcohol, then the color doesn't change. Yes, is this point is clear to everyone? Okay. Now, what they are saying, complete the equation to show the reaction of excess sodium with citric acid. See, they have mentioned excess sodium. Show the skeletal structure of the product. So this is the important thing, important instruction they have mentioned over here to write the skeletal structure. So you may write structural skeletal structure. Okay. Now, when we talk about sodium, that's you must remember that sodium reacts with both alcohol and carboxylic acid. Okay. So let's make the structure. What would happen? The 1 minute, please. Yes. What would happen? The H that of carboxylic acids and the H of alcohol is displaced by sodium. So the whole structure remains same, but we don't put an H wedge where that are bonded to oxygen. And instead of H, we put Na. So how many sodiums are used? 4 sodium. How many hydrogens are displaced? 4 H are displaced. So 2 moles of hydrogen gas would form. Yes, is this clear to everyone? Okay. Now, use the information in the table to deduce the skeletal formula of X, and they have given you the molecular formula C3H6O3. Draw the skeletal formula of X in the box. Label the chiral center of a compound X with an asterisk. Okay. So X is C3H6O3. What else we know about X? That X have a carboxylic acid, right? X have a alcohol, but that alcohol is either primary or secondary, and further X have a chiral center. So on the basis of these, we can conclude or deduce its structure. So let's start. There is a carbon. If I'll go for a, you know, chiral carbon, let's consider an OH is bonded to it and H is bonded to it. Then total I have a three carbons. So I made all the three carbons. Okay. So I have shown the alcohol in it. I have completed the three carbons. I have just shown one oxygen. So if I consider this one or this one a carboxylic acid, so see, three hydrogens are shown, right? Now, three oxygens are completed, three hydrogens are shown, three hydrogens are left. So if I'll make three hydrogens over here, so see, this carbon becomes a chiral carbon. We have a secondary alcohol as well, and we have a carboxylic acid. And if you count the atoms, you will end up getting this formula. Is this clear? But I have to show the skeletal formula over here as the examiner said. So there are three carbons. So I can make three carbons like this. This central carbon have a OH bonded to it. This carbon have a carboxylic acid. And this carbon is CH3, so I keep it as it is. So this is the skeletal formula of compound X. Is this clear?
Yes, sir.
Okay. Now what they are saying that explain why compound X reacts with acidified dichromate but citric acid does not. So if we are discussing this thing as it is an oxidizing agent and we figure it out that X have a secondary alcohol which undergo oxidation to give you ketone, and citric acid have a tertiary alcohol which never oxidizes. Okay, so I can write that citric acid contain tertiary alcohol which does not undergo oxidation while X contain secondary alcohol which undergo oxidation. Is this clear to everyone?
Yes, sir.
Okay. Now look at the C part. Compound X is one of a pair of stereoisomers. Okay. And as we seen that it have a chiral center, there are two types of stereoisomer. One are geometrical and the other one are optical. So as it have a chiral center, which means that the stereoisomer that X can exhibit would be optical isomers. Stereoisomerism occur when a molecule has at least one of the two key features. State two key features that give rise to stereoisomerism. Okay, if it have a chiral center, then optical isomerism is arised. So I will write that chiral center, and further I can elaborate a carbon which is bonded to four different groups. Number two, the other stereoisomer is geometrical isomer, and which is exhibited by the molecules having carbon-carbon double bond. So a carbon-carbon double bond and each double bonded carbon is bonded to two different groups. Then it geometrical isomerism can also be seen. Now,
सर
next
इसकी
part.
डबल बॉन्ड थी, जियोमेट्रिक आइसोमेरिज्म होती तो स्टीरियो आइसोमेरिज्म से अलग है ना वो?
No, stereoisomerism are of two types. Stereoisomerism can be geometrical. One type is geometrical and the other type is optical. These two types are the subtypes of the stereoisomerism. It is different from geometrical isomerism is different from optical, but both are stereoisomerism. Okay, Shahan?
ओके सर.
A structural isomer of compound X does not fizz when added to a sodium. Explain what is meant by the structural isomer. So we know compound or a molecule having same molecular formula but different structural formula, then that compound is considered as a structural isomer. Okay, so here we have ended the paper. This paper is quite easier than the last one because we have ended in the two sessions. Okay, so I will going to share the next paper either tonight or tomorrow, and inshallah we have our next session tomorrow in the night. Okay, so see you everyone tomorrow. Take care everyone. Allah Hafiz.